This presentation is going to cover the rocks chapter for historical geology. We will discuss the three types of rocks in this presentation. The learning objectives for this chapter is to introduce you to the three main types of rocks and how they relate to each other, how they're formed, and their basic characteristics. If we were in a physical geology course, which is also an introductory level course, we would go into each of these rocks in more detail. But for historical geology, we're putting all of the rocks into one chapter. The rock cycle describes the process by which the rock components of the crust slowly but constantly change from one form to another. It's a cycle that is driven predominantly by two forces. The first one being the Earth's internal heat, which helps move material around in the core and the mantle and leads to the slow but significant changes you see in the crust through the process of plate tectonics. The second force that impacts or drives the rock cycle is the sun, which powers the hydrological cycle, or the hydrosphere, which involves water. Moving water, as well as wind and air, all help shape the Earth's surface and impact the rock cycle. So the rock cycle is still active on the Earth today, and it has been for a long time. And it's because our core is hot enough to keep the mantle moving. Our atmosphere is also thick enough to support circulation. And we have liquid water. So all of these three things allow for the rock cycle to continue. On other planets, like Mars, for example, it was very significant when it was identified that the dunes on Mars were actually moving. And I actually had an internship where I was looking at very specific or small location of dune fields on Mars, and I was able to identify the process of saltation, which is the movement of sediments being carried by wind. And that was a significant finding because it indicated that the atmosphere had to at least be thick enough to move material. So that thickness of the atmosphere is very important, is a very important aspect of the rock cycle. When we look at the rock cycle, we can start at any point, but it makes sense to start here with magma. So magma is molten rock material, and when it cools, it becomes a rock that's known as an igneous rock. And there are two types of igneous rocks. You have igneous rocks that cool very slowly, and those are called intrusive. And you have igneous rocks that cool very quickly, like the ones that you get from volcanic eruptions, and those are called extrusive rocks. So you have the magma, it cools, you get either intrusive or extrusive rock, and then let's say that rock is buried. When it is buried, a rock will experience increased pressure and increased temperature. And when you have that in increasing amounts, you will get a metamorphic rock, which is a rock that used to be something else that is becoming something new. So a rock that has been altered from its previous form and state. And it needs to be changed significantly enough, like the structure of the rock changes and different crystals can start to form in a metamorphic rock that make it a metamorphic rock and not just a slightly altered version of the rock it was previously. So that is one way that the cycle loops. But let's say, okay, we get back to magma, you have a extrusive rock, and then it undergoes uplift, and that uplift, due to plate tectonic movements, leads to outcropping. And an outcrop is when you have a visible rock face at the surface. So a formation of a rock body or rock unit that is exposed at the surface. And you usually, I mean, depending where you are, but you usually only see a portion of a rock layer exposed at the surface. You don't see like the entire thing at the surface typically. So you have an outcrop, and once you're at the surface, you are exposed to um, the impacts of water and the hydrological system. So that means weathering and erosion. And it's not just water, wind as well plays a role here. And again, that's where the thickness of the atmosphere comes into play. So you have an outcrop, you have erosion, you have weathering and erosion, and that outcrop gets broken down into smaller pieces, and those pieces are transported, carried away, and deposited somewhere else. So you have an accumulation of sediment that occurs. That accumulation of sediment will be buried, and as it is buried, it is compacted. And as it is compacted, it starts to become cemented. So this here is describing a process of lithifying the rock. Lithification, or the process of diagenesis, is the term, is the process for that burial, compaction, and cementation that will bring, or that will make sediment turn into a sedimentary rock. So that's how you get that third type of rock, is a sedimentary rock. Now at this point, that sedimentary rock can uplift into an outcrop, and that's how we can repeat this cycle of erosion, sediment, sedimentary rock, and again. Or that sedimentary rock can continue to be buried, turn into a metamorphic rock, and at which point it too can be uplifted, becomes an outcrop, it gets eroded, transported, deposited, sediment, and so on, right? Or that metamorphic rock can continue to be buried, and it gets buried to a degree where the pressure and temperature are so great that it creates melting. You have molten rock material, at which point you've created magma. And so that is how you go through the rock cycle. For igneous rocks, you need magma, which is molten rock material. And the temperature of that magma can range between 800 degrees Celsius to 1600 degrees Celsius, depending on where you are within the mantle and where that magma forms. Magma can either cool slowly within the crust or quickly. When it cools slowly, we call that intrusive. It is also called plutonic because the structures that form from large igneous bodies within the crust that cool, they're called plutons. So intrusive is a synonym for plutonic igneous rocks. So you might hear a plutonic, that just means intrusive. Then you have extrusive. Extrusive means it cooled on the exterior, on the surface. So these are that magma that made it to the surface. So it became lava. It becomes lava when it is exposed to the surface. It cools quickly. And we also call that, a synonym for that is volcanic, and that should make more sense because they typically come from volcanoes. So extrusive, you might hear an igneous rock referred to as extrusive or volcanic. Just know that it means the same thing. Igneous rocks are classified by two main criteria: composition and texture. So let's first talk about composition. Composition is basically divided into four categories: ultramafic, and you see them here, ultramafic, mafic, intermediate, and felsic. So these are the four categories of composition that an igneous rock can have. These categories refer to differing amounts of various elements like silica, potassium, sodium, calcium, iron, and magnesium. And these elements are found in the minerals that make up the rocks. So mafic refers to the overall composition. Mafic refers to an overall composition that is high in magnesium and iron. The minerals that compose mafic rocks are referred to as ferromagnesian minerals, meaning that they are enriched in these elements. And on the other side of the spectrum, basically the opposite of mafic is felsic. And felsic refers to the overall composition being enriched in the feldspars minerals of sodium-rich plagioclase and potassium feldspar, as well as silica. So silica is an very important one here, which is found in quartz. So it is important to note that these groups do not have really sharp boundaries in nature, and these four categories, you can think of them as like a spectrum. So using the Bowen's reaction series alone really doesn't allow us to classify the rocks beyond their composition. So in the next slide, we'll talk about texture as well. But if we're just focusing on composition, there are two parts of this plot. You have the discontinuous branch and the continuous branch. And as you cool, as your temperature goes down, these minerals are coming out of solution. They're crystallizing out of the magma. And first you have olivine, then pyroxene, then amphibole, then biotite, and then potassium feldspar, muscovite, and quartz. And on the other side you have the continuous branch, where you basically have plagioclase throughout this whole cooling process. But what's changing about the plagioclase is how much of either calcium or sodium are in it. One end member is anorthite, which is very calcium rich, no sodium, and the other end member of plagioclase feldspar is albite, which is sodium rich. This here is a diagram that uses the information from the Bowen's reaction series to show you what visually the distribution of different minerals across the four categories of igneous rock composition classification. So if you're looking at felsic, we have the less dense minerals that you see in the continental crust. So think a composition of like granite. You have a large percentage of potassium feldspar. You have quartz. Your plagioclase feldspar is going to be rich in sodium. You'll have a little bit of biotite and a little bit of amphibole. With your mafic, you have no potassium feldspar. You do not see any quartz. You have plagioclase feldspar, but it is rich in calcium. You have pyroxene and olivine. And then your ultramafic is going to have some calcium-rich plagioclase feldspar, pyroxene, and olivine. And some ultramafic rocks, really you only see olivine in it. Now, I skipped over intermediate because it's intermediate. It falls right in between felsic and mafic. And this is really a gray zone. Like you see how these lines are dashed here. It's because, classifying these rocks in the real world can get a little tricky, like at what really is the cutoff between a felsic and an intermediate. It's typically pretty clear if you have a felsic versus a mafic, but when you get a rock that's like 50-50, it's hard to tell. It kind of falls in this gray zone. But yeah, you get a little bit of everything in the intermediate. And a common rock that is categorized and is kind of the primary example of an intermediate rock is diorite, and its extrusive version would be andesite. So this row here that you see are the intrusive igneous rocks with the same chemistry here. So you have granite and rhyolite. So this is what a magma that had this composition, if it cooled slowly underground within the Earth's crust, it would look like this granite. But if it came out of a volcano explosively and cooled very quickly, it would look like this. It would be a rhyolite. And then the same goes for diorite and andesite, gabbro and basalt, and then peridotite and comatite. Igneous rock texture refers to the crystals that you see. So if you can see individual crystals clearly, we call that a coarse-grained texture or phaneritic texture. And this is a texture you would see with an igneous rock because the magma had time to grow crystals. But in the example of lava extruding onto the surface or near the surface where it cools very quickly, the igneous rock is called extrusive, right, or volcanic, and that extrusive rock will have a fine-grained texture or aphanitic. So you have phaneritic, coarse grain, or aphanitic, fine grain. And when you have an aphanitic texture, what you have are grains that are too small to see with the unaided eye, meaning that just with your eye alone, you wouldn't really be able to distinguish individual crystals. You maybe with a hand lens you can start to see some crystals, but it certainly would not be as easy to see as with a granite, for example. Sometimes you can have extrusive material or extrusive lava that cools so rapidly that it doesn't even develop crystals at all. And these are non-crystalline rocks and non-crystalline material, which is known as volcanic glass, and a common version of this is the rock known as obsidian. So once you know the composition and you have an idea of the texture of the rock, then you can use that information to classify the igneous rock. And so this is just the bottom portion of the diagram I showed in the previous slide. And so you should be familiar with the general composition of the granite or the rhyolite, the diorite, andesite, gabbro, basalt, or the peridotite and comatite. Let's now move on to sediments and sedimentary rock. Now, sedimentary rock formation is a cycle unto itself. There's a process here. So the cycle begins with the exposure of a pre-existing rock to, quote, agents of weathering and erosion. So that would be things like wind, water, ice, things that would cause weathering conditions and facilitate erosion as well. So erosion is the removal of weathered material. So you have weathered material, meaning that the material is broken down. It breaks down the rock, either chemically or physically or both, but the erosion is the removal of that material from that area, so it's being brought somewhere else. Now, the effects of weathering on pre-existing rock can be physical and chemical. And physical weathering is basically the physical disintegration of the rock. So the breaking down of solid rock into smaller pieces. And the more you break down the rock, the more rock is broken down, the more it erodes, because as a rock is withered, more of its surface is exposed, and if more of its surface is exposed, then it will wither more. So it's like a positive feedback. It keeps on increasing. The weathering keeps on increasing. Chemical weathering, on the other hand, produces changes in the chemistry of the mineral within the rock that is being weathered and eroded. And these changes can result in a new mineral formation through the adding of elements or the subtraction of elements. And this, further disintegrates the rock by chemical decomposition. And the dominant agent involved in both physical and chemical weathering is water, because water is a universal solvent, and water acts as an agent of change, both introducing elements that can interfere with the chemistry of the exposed minerals, and also acting as a flux that physically removes weathered rock material and ions to a different, can transport it out of that area or that system. Weathering produces particles of sediment, and plus, not just sediment, but plus ions. So carried in the water, dissolved in the water. The sediment is transported, that it can be transported and deposited, somewhere close or somewhere far, depending on the system. But following deposition, the sediment is buried, compacted, and cemented. And that's that process I described as diagenesis. And collectively, these processes serve to lithify the sediment into a rock. Now, the ions in the solution being carried in the water that, chemically weathered a pre-existing rock can have, certain impacts. It can be used in cementing the sediment. Those ions can be used in the cementing. It can also be extracted from the water as well and used by biology, plants, animals. It can be used and consumed by animals that then use it for, they're creating skeletal material. But another thing that can happen is the formation of a different type of sedimentary rock, which is a sedimentary rock that is produced by precipitated material. And so you can have precipitation from the water and the development of a sedimentary rock that way. Now let's first talk about clastic sedimentary rocks. And these are rocks that are basically made up of pieces from other rocks, pieces that came together from weathered bedrock and cemented together to make a new rock. Now these pieces have different names. They can be called clasts or detritus/detrital. So detrital sedimentary rocks or classic sedimentary rocks, it means the same thing. And the clasts are basically describing the pieces, the grains that make up the sedimentary rock. And sedimentary rocks are essentially defined by their class. So the characteristics of their class are used to define the type of sedimentary rock it is. The clastic sediment is also sometimes referred to as siliciclastic because it is derived from the rocks of the crust, which we know is largely composed of silicate minerals of igneous rocks. So clastic or detrital rock is classified and named based on not just the size, like I was just saying about the class, but also the composition. So that's an important one. There are various sizes from boulders to clay, and when I say the term clay in this context, when we're talking about sedimentary rocks or sedimentology, clay refers to a grain size. Now, there is a classification chart for the classic sedimentary rocks in the textbook. There's a lot of text in there, and I did not include it in the slides because it was just too big. You couldn't really read the text, but take a look at that classification chart because it has a lot of information on there. But basically, you have the classification and description of the various clastic sedimentary rocks there, and it'll walk you through each one. Then you have chemical, biochemical, and organic sedimentary rocks, and we're lumping all of these all together. We could focus on each one in more detail, but our textbook chapter doesn't So we'll keep it high level here. So your chemical sedimentary rock is formed by processes that do not directly involve mechanical weathering and erosion. They involve chemical weathering. So chemical weathering contributes the dissolved ions in the water that ultimately form the various rock types. Now, inorganic chemical sedimentary rock is made of minerals that are precipitated from ions that are dissolved in the solution. And inorganic chemical sedimentary rocks form in these environments where you have high concentrations of ions and you have as well as dissolved gases, higher temperatures, and pressure changes, which cause minerals to crystallize. So a lot of times, I just listed a few of the things that you need in the environment, but sometimes you just need a change in one of those things to facilitate precipitation. So sometimes just, a drastic change in temperature can cause things to come out of solution. So it just depends on the environment and what is in there, what ions are available in the solution, and then what is the change that causes that initiation of precipitation out of the solution. With your biochemical sedimentary rock, this type of rock is formed from shells and the bodies of underwater organisms like corals, and the living organisms extract chemical components from the water and use them to build shells or other body parts. A lot of time that's going to be predominantly calcite that you see coming, formed in this way, biochemical sedimentary rock. And then you have organic sedimentary rocks, and these contain the remains of organic material that has undergone the lithification process. So the source materials are usually plant and animal remains that are transformed through burial and heat. And this is where most of our fossil fuels come from. So coal, oil, and methane or natural gas are formed this way. They're sourced from an organic sedimentary rock. So I touched on how we describe class and thereby sedimentary rocks made of said class by their size. But we also look at the rounding of the class. So how angular are the edges on the class? And that angularity plays a role in how the rocks are classified, because the rounding of the class tell us something about the sediments that made up that sedimentary rock. So if you have a grain that has very sharp edges, you have a sedimentary rock that's made from grains that have very sharp edges. Those sharp edges tell you that that sediment was deposited very close to its source. Because when sediment is transported, it comes into contact with other surfaces, other sediments. When that happens, the edges on those clasts become more rounded, become softer. So the rounder the grain is, the further it was transported. That's why the sand you see at the beach is so, we call that well-rounded. That's kind of one spectrum of how we would describe the roundness of the grains, well-rounded. And then the other end member would be, very angular, highly angular grains. But that is used. It's not really discussed too much in the chapter because, like I said, they kind of keep this chapter very high level. But I thought that was important to share because in historical geology, one of the main rock types that we are looking at is going to be sedimentary rock, because that's where fossils are preserved, is in sedimentary rock. And I thought that would be good for you to have that understanding. So I'm just mentioning it here with a picture of conglomerate because conglomerate is a special type of rock where you have a mix of grains, but the mix of grains includes grains that are pretty well rounded. So it's a coarse grained clastic rock because it has very high um, the grain size, the clasts are very large. Um, but you can have, pretty rounded clasts as well here. And so conglomerates form from the consolidation and lithification of gravel, and conglomerates are typically poorly sorted. So that's another way of describing sedimentary rocks too, is the sorting style. So for example, conglomerate is a textbook example of poorly sorted. And what does that mean? It means that you have a mix of different grain sizes. If you have a rock where all the grain sizes are the same, then we would say that is well sorted. Breccia is similar to conglomerate in that it has a wide range of class sizes and it is poorly sorted. However, you'll notice that with breccia, these clasts are very angular. And the book doesn't really give you much interpretation on or explanation on where you would see this. But when you see breccia, think of fault zones. So an area where rocks were broken up, but then they didn't move. They didn't go anywhere. With the conglomerates, think of environments that have a mix of a wide range of sediments, but they were moved very far. So like streams, braided streams that maybe flood periodically. So, they get moved, they settle, they get moved, they get settled. There's a wide range of energy because in order for grains to be moved, you need energy. And when you have a wide range of grains, you have a wide range of energy going through the system. In the slide deck, I put slides for the different rock types, but I'm not going to go through each one. You go ahead and take a look at them. I included them in the notes. We're going to move on to metamorphic rocks and metamorphism. So metamorphism is the change that takes place within a body of rock as a result of being subjected to increased pressure and temperature. In most cases, but not all, this involves the rock being buried beneath other rock where, it would experience these changes in their condition. So metamorphism typically includes the recrystallization of minerals plus the formation of new minerals and different textures through, however, so you get new minerals, you get recrystallization, but the thing about metamorphic rocks typically is that the overall chemistry stays the same as the original rock. And when we're talking about metamorphic rocks, that original source or that original rock, we refer to that as the parent rock or the source rock. Another term for that is the protolith. And proto just means first, lithos rock, right? So the protolith, the source rock, parent rock, it really depends what area of geology you're talking about. Because if you're talking to a petroleum geologist and you tell them source rock, they're going to be thinking that's an organic sedimentary rock. So you just have to know your audience. But typically when we're talking about metamorphic rocks, I always called it a parent rock. But protolith is also used. But most metamorphism is the result of tectonic forces during mountain building events. Plate collisions, especially continent-to-continent collisions, introduce really high amounts of stress and heat. And that's because one plate can't really subduct under another. You can't push continental crust into the mantle. So instead, you just get an incredible accumulation of stress and heat. and that can take place over a very large area because the colliding continental masses have nowhere to go, so it can expand a very large area. And these are the primary factors or conditions that are needed for that, dramatic change that occurs and basically takes you from a protolith to a metamorphic rock. There are two types of metamorphism. You have contact metamorphism and regional metamorphism. And so regional metamorphism occurs over a wide area of the crust. It can be, hundreds to thousands kilometers across. And this typically results from the collision and compression of tectonic plates. It can have a big impact on continental crusts, but also oceanic crusts that might get caught up in the collision. You typically don't see this with like just ocean collision, for example, because with ocean collision you typically get subduction, but with continent collision you typically have building up of the crusts. And here is where you get, an immense amount of stress and thickening happening. So regional metamorphic processes really can affect, of course, the entire thickness of the crust, but also the upper mantle. And yeah, this can cause, a lot of change in the pre-existing rock over a very large area. Now with your contact metamorphism, this here is a little simpler and not as expansive as regional metamorphism. So this affects a pre-existing rock by basically baking them through a contact zone. So you're basically heating the surrounding rock through contact with molten material. And that contact is either initiated by intrusion of the magma or extrusion of lava onto the surface. Now, intrusion can occur very deep in the crust and involve, large areas and large areas affected by heat associated with these like really big magma chambers. If you have a big, like here, a big magma chamber here, right? So along the edge basically along the edge of that magma chamber and any diapirs coming from that magma chamber, you will have contact metamorphism or, a bake zone. When we're talking about the main factors that control metamorphic change of a, pre-existing rock, one of the first things that you're going to want to know, and it's going to matter and probably have the biggest impact, is going to be your starting material. So what is that parent rock? What is the protolith? The parent rock is what exists before the metamorphism starts, and any type of rock can be a protolith, including pre-existing metamorphic rock. Sorry about my dog. The critical component of a parent rock is its mineral composition, because that is not going to change a whole lot when you undergo metamorphism. The overall chemistry composition stays the same. And so, yeah, the mineral composition for, what are all the minerals that are already in place, because that is what's going to be rearranged essentially. So when a rock is subjected to these increased temperatures and pressures, certain minerals may become unstable and begin to recrystallize and change in size and orientation. It's been mentioned a number of different times and in different ways. By this point, you have an understanding that temperature plays a very big role in the creation of metamorphic rock, as well as igneous material. So, temperature is really important here. Minerals remain stable over, certain specific ranges of temperature. So like quartz, for example, is stable under all surface environmental temperatures and will remain stable all the way up to 1800 degrees Celsius. But on the other hand, most clay minerals are only stable up to about 150 to 200 degrees Celsius, and above that, they transform into micas. And then feldspars, which is one of the most common minerals in the crust, is stable up to about 1200 degrees Celsius. So having an understanding of mineral stability and also what those temperature ranges are is going to help us, understand the metamorphic process. Pressure is the force that is exerted on the parent rock, and this force can come from burial or it can come from tectonic stresses or both. And like heat or increased temperature, pressure can change the chemical equilibrium of minerals in a rock, and it can change their melting points and when they come in and out of solution. So the pressure that affects metamorphic rocks can be grouped into confining pressure and directed stress. So typically when we talk about pressure, we're thinking about stress and strain. When you hear stress, think of force, the force acting on something. But when you hear strain is the result of the stress. So strain is what happens as a result of the stress. So confining pressure is a key thing to consider when we're talking about pressure in a metamorphic setting. So when you have pressure, right, it can be exerted on a rock that's under the surface simply due to burial, so by things being stacked up on top of it. And when pressure is exerted from rocks above, it is typically balanced by pressure from below as it is being buried. And when you have equal pressure basically on all sides, we call that confining pressure or lithostatic pressure. Now, confining pressure results in equal pressure on all sides, and it is responsible for causing chemical reactions to occur, just like heat. That pressure can basically cause chemical reactions, increase pressure, because you're exerting a force onto the atoms. Now, differential stress is an unequal balance of forces on the parent rock in one or more directions. So it's not like confining, it's not equal, it's not pressure on all sides, it's going to be differential, meaning the stress is not going to be equal all over. And differential stress can modify the parent rock at a mechanical level. It can change the arrangement, the size, and or the shape of the mineral crystals. So you're not necessarily creating new minerals here, but you're changing what's there, what's already there. And this actually results in a change or a distinctive texture that is left behind called foliation, which this is a prime example here. You have a granite, there was differential stress applied to it, and you get a rock that is called gneiss. Now, differential stress produces these rock textures, and what's distinctive or characteristic about foliation is that they're basically a parallel alignment. It's very visibly, it's easy to spot. Usually these parallel alignments are very obvious and easy to spot. And this happens in response to differential stress, where the mineral crystals are rotated and they change their orientation in the rock. This is a process of recrystallization in a solid state. So the rocks never actually become molten. The atomic structure of the mineral will respond to the stress, and the atoms will migrate within the structure in response to the stress. Yeah, so it happens in solid state, so it's never molten. That's an important thing to keep in mind here, is that um, it doesn't become molten. Um, this recrystallization also leads to minerals increasing in grain size, usually as the atoms migrate from, one area of the rock experience high stress to an area of low stress. And there is if you look in the textbook, there's some like interactive samples for you to look through that I think are really worth kind of you zooming in and looking at some of these fine structures. Fluids, primarily water, is very important for metamorphism because, well, for one, it's present. It's the main fluid that's present within rocks and in the crust. It's everywhere. But just the presence of water really changes the behavior of minerals. And that presence of water, it acts as a catalyst, and it can increase the rate at which these metamorphic reactions or recrystallizations are actually taking place. Time is a key ingredient for metamorphic reactions because it happens over very long periods of time. I'm not actually familiar with the research that went into this calculation, but according to the textbook, the it's estimated that a change, like a formation of a new mineral within a metamorphic rock, and that new mineral being about 1 millimeter, is estimated to take about 1 million years to form. So this is a very, very long time, and it's a difficult thing to study, obviously, in a lab. And so, these rates of metamorphism are very slow. The rates of tectonic movement is also very slow. So it can take a very long time for you to have, a mountain range that forms, and then for that mountain range, to thicken so much that you get metamorphism, regional metamorphism, and then you also have the uplift and erosion of that rock to then be exposed. It can all take a very, very long time. So now looking at specific metamorphic rocks, again, there's a metamorphic rock identification chart in the textbook, and I didn't put that on the slide because it was just too big, and the text wasn't legible if I put it on the slide. So make sure you look through that. But yeah, so metamorphic rocks are classified based on two characteristics: texture and composition. Texture being one of the main kind of categories or classifications of metamorphic rocks, and it's basically just two: foliated and non-foliated. So your foliated is going to have foliation, like we talked about. Foliation is caused by differential stress, right? And that causes that distinct alignment of the minerals. These foliated metamorphic rocks are named based on their style of foliation. Your non-foliated rocks are either not subjected to that differential stress, or it could be that the dominant mineral that's within that rock just does not tend to display any alignment. And we made it to the end of this presentation. Like I mentioned in the beginning, this chapter is more of a survey of the rock types. So we talked about the three main rock types, how they're classified, some examples of some or some distinguishing characteristics of each one. We also hit on the rock cycle and how that can relate to the rock cycle to the three different rock types as well. You will see that the slide deck for this chapter has more slides than is included in this presentation, and I just included pictures of individual rocks for your reference, but you can also look at those in the textbook, and then you'll see them as well in the lab manual. So thanks for listening.